Sample preparation is an important part of providing reliable and reproducible results. My name is Thao Gastaldo, and I'm part of the applications team here at Micromeritics. This presentation will cover sample preparation and how to start an analysis on a Micromeritics Physisorption instrument. We will cover the materials that are needed, how to weigh the samples, degassing the samples, discussing the different degas options, including how to attach the samples to the degas unit and how to start a sample analysis. Lastly, we will look at some examples of how sample preparation affects test results. We will first need sample tubes. There are several options available depending on the instrument, with differences in stem outer diameter, bulb size, flat or round bottom bulb, stem length, and straight wall or bulbous tubes. To minimize uncertainty in the test results, smaller stems and bulbs can be used to reduce free space error or if limited sample is available. The larger tubes are easier to fill and clean, and the opening is large enough to fit in a glass funnel for adding sample. Flat bottom sample tubes help with analysis speed. Compared to round bottom, total test time is reduced by a third for mesoporous materials. This is because since the bottom is flat, more of the sample is spread out compared to cupped in a round bottom tube. More of the material touches the glass, which is being cooled by the cryogenic liquid. In turn, the sample cools down faster, reaches thermal equilibrium faster, leading to reduced analysis time. A stopper is used to cap the sample tube during transfer from the degassed unit to the instrument. For samples that are microporous or sensitive to air or moisture, a transseal, check seal, or seal frit can be used depending on the sample tube. A transseal allows the sample to be under vacuum during the transfer. A check seal and a seal frit will seal the opening of the tube, preventing the sample from being re-exposed to the atmosphere. The seal frit also has a secondary filter to prevent powder from contaminating the system. The sample is now ready to be weighed. First, tare the balance. Weigh a clean sample tube with the stopper. If using a transseal, the sample can either be weighed after degas or after analysis. If the sample is to be weighed after degas, make sure to first evacuate the empty sample tube with the transseal. This is not needed if the sample is to be weighed after analysis, as the sample tube will be backfilled to atmospheric pressure. If a hollow glass filler rod or check seal with a hanging filler rod will be used during analysis, also weigh the filler rod now. This mass will be recorded as the empty sample tube mass. Use enough sample to minimize weighing error and to ensure the sample is representative. How much sample to use is covered in Tech Tip 14, which is available on Micromeritics' website and will also be briefly covered next. Add sample to the tube and clean the sample tube walls to ensure all sample is in the heating zone during degas. Reweigh the tube with sample and record this as the before degas mass. Tech Tip 14 refers to the minimum total surface area in square meters that's needed with a maximum percent uncertainty. This will depend on the instrument, the sample tube size, adsorbate, and whether free space is measured or calculated. For example, if a sample in a 12 millimeter outer diameter tube is to be analyzed on the 3-flex with nitrogen with free space measured, and there is 100 square meters total surface area in the tube, the maximum uncertainty of the data is 0.38%. Tech Tip 14 goes into more details how these values are determined, and the document is available for viewing on Micromeritics' website. An important step in sample preparation is to degas the sample prior to analysis, as it can greatly impact test results. The purpose is to remove any moisture or atmospheric contaminants from the sample's surface, allowing for the analysis gas to adsorb onto a clean surface. This is done by applying heat to the sample for an amount of time while pulling a vacuum or flowing an inert gas. If the sample surface is not free of contaminants, this can lead to lower results than expected. Ensure the temperature being applied is safe for the material as to not change the sample's surface. The degas time also needs to be long enough. To determine a safe temperature for the material, refer to its SDS, literature value, or perform a thermogravimetric analysis. If degas conditions are unknown, this will require a little bit of trial and error. Multiple sample tubes can be prepared, for instance 3, and apply different degas temperatures such as 100, 200, and 300 degrees Celsius. The degas time should be the same for all, for example, half an hour. If the result, such as surface area, is the same at 100 degrees Celsius and 200 degrees Celsius, but it goes down at 300, this means that the sample may be damaged because too high heat was applied. 200 degrees Celsius would be an acceptable degas temperature to use. If degas time is unknown after figuring out the degas temperature, multiple sample tubes would again be prepared. Vary the degas time, for example, 1 hour, 2 hours, and 3 hours, while keeping the degas temperature the same. The degas length that gives the highest surface area with the shortest amount of time should be selected. Pre-treating the samples in an oven before degassing can help reduce degas time if the material is known to hold a lot of moisture. In general, if a low temperature is used, then degas time should be longer and vice versa. These are some standard degas conditions that are used by our labs for a few of the materials we often test. Samples such as activated carbon and biochar are degassed at 200 degrees Celsius to 300 degrees Celsius overnight to properly remove any contaminants. For materials that can withstand higher temperatures, such as pure metals, they can be heated to 400 degrees Celsius for an hour. With materials that are more sensitive to heat, such as pharmaceuticals, it would be safer to degas at ambient temperature for an extended amount of time, such as overnight. Micromeritics offers a few degas options, both flow and vacuum systems, including the Flow Prep, Vac Prep, and Smart Vac Prep. Samples can also be degassed on instruments, such as with a couple in the ASAP series, and secondary degas options are available as well. The Flow Prep is a manual degas unit that flows dry nitrogen with 6 sample heating ports in the back and 6 cooling stations in the front. Temperature can be set up to 400 degrees Celsius with a control pad. The heating ports are dependent. Only one temperature can be applied, and this is shared across all ports. Gas flow is enabled by flipping a switch that opens the port valve. A flow control valve can be added to adjust gas flow. The needle that delivers gas to the sample should be placed at the bottom of the sample bed. This can be done by gently tilting the sample to one side, insert the probe, then gently tilt the sample back to cover the needle. Prior to pushing the needle through the sample, gas should be flowing to create back pressure, preventing the sample from clogging the needle. The sample tube is then placed into the heating port. The Vac Prep is another manual degas unit that uses a vacuum system. Degas can be performed for up to 6 samples and with 6 cooling stations in the front. The system's vacuum level is displayed on the instrument's vacuum gauge. A control pad is used to set temperature up to 400 degrees Celsius and is shared across all heating ports. The knob is turned downwards towards vac to evacuate the samples. After degas is complete and the samples are cooled, the knob is turned upwards towards gas to backfill with dry nitrogen. Turning the knob to the left closes the valves. Sample tubes are connected to the Vac Prep with the use of a connector nut, ferrule, and O-ring. The tube is then placed into the heating port. Both the flow prep and vac prep use isothermal shield spacers, which are designed to hold the sample tubes in the ports. These spacers cover the lower portion of the sample tube to maintain a uniform degas temperature across the sample. The Smart Vac Prep is an automatic degas unit controlled through the use of software that uses a vacuum for up to 6 samples. Each port can have unique parameters for controlling evacuation rates, times, and temperature up to 450 degrees Celsius. Heating mantles independently apply temperature to each port. Ports can be programmed with unique sets of degas conditions. These conditions are applied to the sample through the use of the push button, controls located above the sample ports. Degas automatically terminates after completing all steps. Status lights are located on the front, which indicate what the unit is doing. A red light indicates that the port is heating. A yellow light means the port is cooling down after being heated. A green light indicates the port is at room temperature. A blinking light is when the port is under vacuum. A solid light is when the port is at atmospheric pressure. Degas conditions for the Smart Vac Prep can be programmed in the SMP or sample file under the Degas Conditions tab. The system will undergo 2 stages for degas, evacuation, and heating. The backfill sample tube option should always be checked unless you're using a transseal. Always backfill with nitrogen so the samples are not removed under vacuum, which will pull atmospheric contaminants into the tube and back onto the sample. Backfill can be done automatically after degas by the system. Wait for operator will keep the samples under vacuum, and the user can manually backfill when the samples are ready to be transferred to the instrument. The following options set the pressures for degas and the initial heating step. Evacuation rate specifies how fast gas is being pulled out of the sample initially from ambient pressure. Lower this rate if your material is fluffy or fluidizes easily. Unrestricted evac from is when the sample's pressure reaches this target. The Smart Vac Prep will stop evacuating the sample in a systematic manner or controlling the evacuation, and a direct path to the vacuum will be open for faster evacuation. If the sample is a chunk or solid, this value can be set high. If the sample is light and fluffy, this value can be lowered. Vacuum level specifies the pressure level the Smart Vac Prep should evacuate to. Evacuation time refers to how long the system will hold at the entered vacuum level. Temperature ramp rate is how fast the temperature will ramp while the sample is going through the evacuation phase. Target temperature is the set temperature for the initial evacuation phase. For hold pressure, if during temperature ramp the pressure exceeds this value, the system will stop ramping to the target temperature. It will hold the sample temperature constant until the pressure falls below this value. This prevents damage to the sample structure due to sample outgassing rapidly or vapor coming off the sample too quickly. Next is the heating phase of the degas. Target temperature, temperature ramp rate, and hold time can be entered. Insert creates a line above the currently selected line in the box. Append adds a line below. Delete removes a specific row, and clear clears the entire table. To attach the sample tube to the port on the Smart Vac Prep, place a connector nut, ferrule, and O-ring on the tube. Gently slide it into the port, then tighten the nut. Place the heating mantle over the bottom of the sample tube and secure it with a metal clip. Samples can also be degassed on instrument on the ASAP 2020 Plus and ASAP 2425. The sample preparation ports use a vacuum for degas and can be controlled using the instrument software. The degas ports operate independently from the analysis ports and from each other. Each can be programmed with unique parameters for controlling evacuation rates, times, and temperature up to 450 degrees Celsius. Heating mantles independently apply temperature to each port, and degas automatically terminates after completing all steps. Parameters to set up degas on the ASAP 2020 Plus and ASAP 2425 are similar to the SmartVac Prep and can be programmed in the SMP or sample file. Some materials require additional preparation after they have been degassed, such as microporous materials. The 3-Flex instrument offers an option for a secondary degas that can be carried out in situ or on the sample port. The bulk of the contaminants should be removed using one of the degas units first to prevent damaging the system. The parts needed to perform in-situ degas include a heating mantle shelf, shelf lock, shelf track, a heating mantle lid, and a heating mantle. To use the in-situ degas accessory, first place the heating mantle around the sample bulbs, turn the lock to secure the shelf, slide on the heating mantle cover, secure the cover and slide the isothermal jackets up so they are not touching the heating mantle to prevent damage to the jackets. Lastly, connect the mantle thermocouple and power plug. After degas is complete, the heating mantle must be removed and unplugged before starting analysis or the test will not start. A message will pop up alerting the user to perform this step. To program in-situ degas, open the sample file and navigate to the Analysis Conditions tab. Click on Preparation, and a Preparation Options window will appear. Set the parameters, check Degas in situ, then click OK. When degassing materials, which degas method, vacuum or gas flow, should be employed? The answer is each method is sample dependent. A flowing degas system can be faster at removing surface contaminants than a vacuum system. The vacuum degas system can remove more surface contaminants. The difference in cleanliness is negligible for most non-microporous materials. For microporous materials, if in-situ degas is also used prior to analysis, results will also be similar between the two methods. Focus should be placed on temperature and degas time. After degas is complete, the sample is ready to be reweighed. Tare the balance, weigh the sample tube and degassed sample. If a transseal is used and the sample is to be weighed after degas, ensure that the empty sample tube with the same transseal were evacuated prior and the assembly was recorded as empty sample tube mass. If this step was skipped or missed, the sample tube with the transseal and sample can be weighed after testing is done when it is backfilled to atmospheric pressure. Record the after degas mass. Subtract the empty sample tube mass from the after degas mass to obtain the clean sample mass. There should be a decrease in sample mass observed between before and after degas due to moisture and atmospheric gases being removed from the sample's surface. Place an isothermal jacket down to the base of the sample tube above the bulb. The sleeve is made of a porous material and wicks up the liquid nitrogen to the top, keeping the temperature constant during analysis. Discoloration of the isothermal jacket is okay, and no maintenance is needed. Only replace the isothermal jacket if it is warped or has melted. Isothermal jackets are not needed if analysis is done with water, since water does not evaporate significantly like a cryogenic liquid. Additionally, the isothermal jacket material is hydrophobic. Filler rods can also be used to further minimize free space error. There are a few different options available. Choose one that is most appropriate for your sample tube. When attaching a sample tube to the instrument, place a connector nut, ferrule, and O-ring onto the tube. Make sure to use the correct parts for the specific sample tube. If a check seal or seal frit is used prior to attaching the sample tube, ensure that a seal opener is on the sample port. The seal opener can be installed or taken off by a removal tool. To prepare for analysis, fill the dewar with a cryogenic liquid, typically liquid nitrogen, while wearing proper PPE. Use a dipstick to ensure the liquid nitrogen is filled to the proper level, which is not higher than the circle on the dipstick. This is the top of the isothermal jacket when the elevator is raised. Place the filled dewar on the elevator. Place the shield on the instrument. To start an analysis, in the instrument software, go to unit number that corresponds to the instrument. Select Sample Analysis. Click Browse and navigate to the desired samples. Assign the sample file to the analysis port matching the physical port on the instrument. The Edit button can be selected to review the sample file or make any changes before starting the analysis. Click Start to begin analysis. In the next few slides, we will look at some examples of how sample preparation affects test results. The first example is of an alumina sample with an expected BET surface area of 5 square meters per gram. 2 sample tubes were prepared, one with a filler rod and the second without and less sample. BET surface area of the sample tube with filler rod is closer to the expected value, while the second is lower. The difference is more prominent when looking at the Rocherol transform plot. A second example is comparing the results of a silica alumina sample prepped with and without using isothermal jacket. The sample tube fitted with an isothermal jacket exhibits a nice isotherm with the hysteresis closing. In the isotherm of the sample without isothermal jacket, the desorption curve crosses below the adsorption curve. This indicates that there is more analysis gas desorbing than what was adsorbed. Since an isothermal jacket was not used, temperature in the sample tube was not kept constant during analysis. As the test progresses, the liquid nitrogen level in the dewar is decreasing, causing the free space to change throughout the analysis. The quantity of gas the sample tube can hold is greater at an earlier analysis time. The desorption curve falls below the adsorption curve as a negative effect of this free space change. These results of an LFP, or lithium iron phosphate, powder are comparing proper degas time, temperature, and clean sample prep versus using unsuitable degas conditions and leaving moisture residue on the walls of the sample tube during analysis. For the improper preparation, condensation occurred during the degas process due to the sample being heated excessively and for an extended duration. The walls of the sample tube were also left as is prior to testing. This isotherm is of the sample ran with a proper prep. With a poor sample prep, the resulting isotherm is not ideal and shows negative adsorption. The isotherm is similar to that of a blank, though there is material present in the sample tube. Thank you for joining me today. To learn more about Physisorption or learn about our upcoming training classes, please visit our website at micromeritics.com.